pieces for this place. And I'm just filling in today for Colin, who's got a wedding anniversary. I think he decided he'd better behave himself and do the right thing. So, yeah, he doesn't want it to be his last, that's right, yeah. So we're just going to do a brief talk on, telescopes and binoculars. I'll just give a bit of background. I've got most of the people I can see here, or quite a few of them, would know all about them anyway, but I'll just waffle on, and if I'm wrong, you can correct me. Colin gave me his slides, and I've modified bits and pieces, but the next one is there. Just an acknowledgement. We acknowledge and pay our respects to the Kaurna people, traditional custodians whose ancestral lands we gather on. We acknowledge the deep feelings of attachment and relationships of the Kaurna people to country, and we respect and value their past, present and ongoing connection to the land. I was up at Membray Creek and Mount Remarkable National Park, and I was travelling around the place with the chief ranger there, a guy called Gavin, who's a Aboriginal guy. His roots are more down in the end of the peninsula. And it was interesting, talking about this sort of stuff. And when I go up around Melrose, I feel connected, because a lot of my sort of 2 and 3 generation ancestors were born there. So, yeah, and you get a sense of what Aboriginal people must feel about country. It's just nowhere near as much, but just that sense of this is my place. I feel at home in this area. So, move on. Just a real quick ones on the invention of the telescope. A lot of you probably know this one. There's a Dutch lens maker called Hans Lippershey. He first came up with the idea of looking through 2 bits of glass and realising that he could get things coming closer to him. And the first one that really grabbed hold of it was Galileo. And if any of you know Tony, that's why I put that one there. It's our very own version of Galileo, who's not here today, but looks a lot like that. And if you've ever seen these things in person, they're crazy. And the fact that he was able to, well, before I do that, the basic refractor telescope, refracting means bending the light, was just a, whoops, I'm hitting the wrong button here, that's the one. So just a single objective with a reverse ocular, and they were about that size, about yay long, and you can get up to 20 magnifications in some of them. It's pretty amazing, but horrible optics. The fact that he was able to see things like the craters on the moon. Nobody had noticed or didn't know what the craters on the moon were. They didn't know there were craters there, because if you look at the moon naked eye, you can't see it like that. He noticed something funny happening with Saturn, and apparently around the time he first looked at it, the rings were almost going side on, and he thought that there were strange things happening around Saturn, didn't realise what they were at the time. And of course he saw the phases of Venus, and that's some of his notes showing Jupiter with the little stars either side of Jupiter, and he worked out that they were moons going around Jupiter, and sort of hooked that across to what the solar system must be like. So we've got our refractor telescope, which is pretty basic. This particular one, we've got a objective lens. The objective is the front one, and the eyepiece up the back. Basically the light comes through here, gets bent to a point here, a focal point, and then the eyepiece is like a little magnifying glass. So you're using the magnifying glass to look at the focal plane, and you can look at different magnifications depending on the focal length of your magnifying glass and the focal length of the objective. So the magnification is pretty straightforward. It's the length of the focal length of the objective lens over the focal length of your eyepiece. So if you've got a 1,000-metre objective and a 5mm eyepiece, you've got 200 magnifications. It's all pretty straightforward, but with the early ones, there was a few problems with that. I'll come back to that one. So we've got, most people see a refractor as a telescope. That's what you see in the stores. especially if you go to the general stores and get a cheapy one. They're the most common small one, many of them cheap, readily available. They do give good contrast generally. They can be quite cheap and can also be quite nasty. I've come across a few of those ones. And they're nice and portable. The disadvantage is some of the cheap ones are really poor optics. You look through them and it's hard to actually work out what's going on there. I've seen some of the boxing for some of these ones. I haven't seen so much lately, but they used to do things like 600 magnifications, and they put pictures from the Hubble Space Telescope and all this sort of stuff in from a 60mm objective lens. I think, yeah, right. It probably does magnify something 600 times, but there's no way you could work out what it was. They do have a small aperture, the refractor. I think the biggest one is that one I showed you right at the start. It's a 40 inch. You get any beyond that and they start to, the glass tends to bend a little bit and they just don't do the job. So 40 inch seems to be about the limit you can go. And good quality ones are very expensive compared to mirror ones. That one there's a little Takahashi 4 inch. It's a lot more expensive now than when I bought that one, but yeah, they're crazy prices. You can spend $5 or $6 grand on a 4 inch telescope if you're crazy enough. I didn't do that. Now, one of the problems with the refractor telescope, the one with the lens in the front, is what they call chromatic aberration. And that's because when light comes through a lens, it gets bent by the lens, but the wavelength of the light means that it gets bent in at different angles. So long wavelength light, like the red end of the spectrum, doesn't get bent as much as the shorter wavelength blue of the spectrum. And if you're trying to find a focus which should be around there, you'll find that there'll be colour fringing on what you're looking at if you've got a basic telescope. So a lot of work was done, or has been done over the years, to try and fix that up. The first one was what they call an achromat telescope, where they had two bits of glass at the front, which had different, what they call refractive index. They'd bend the light slightly differently, and so one of them would bend red a bit more than the other one and vice versa. And they would bring the two of the wavelengths to a point. There was a bit of, it wasn't quite right with these ones, but they were a lot better than just the original ones, which were really fuzzy. And if you ever look through one of the early type ones with no correction and just a straight lens at the front, they're not really much fun. Galileo wouldn't have had much fun with his. Then we have the next step up, which is the latest and greatest, the apochromat. Where the achromat brings the red and the blue together, but green sort of is off a bit, the apochromat tries to bring them all to the same point with different degrees of success. So that one I showed you before, the little Takahashi, is a triplet, and there's almost no chromatic aberration in that. It just brings everything to the same spot. Over the last 20, 30 years, they've come up with ED glass, which tends to enable you to bring them to the point a bit better. And so a lot of the apochromats nowadays are a two-piece lens rather than a three-piece, which are cheaper to make. And I know Takahashi have gone to the doublets nowadays, much more than the triplets. So the modern ones have got different types of glass, the crown and the flint, the extra low dispersion ED glass and so on. Some of them you see with HD glass as well, which is basically a type of ED or extra low dispersion. Then we have our reflectors. Isaac Newton is credited with coming up with the idea of reflecting the light rather than having to look through a lens. And if you do that, a reflection, all the wavelengths get reflected the same angle. So you don't have the problem of the chromatic aberration with a reflector. He used speculum metal, which is a combo of tin and copper, I was trying to find a picture I had of one of the early ones of these, and it hadn't been polished, and it's just this grey thing. They had to polish them pretty regularly, but they did do the job quite well. And of course, here's the first one, was this baby, well, that's his second one. It was only about 3-inch, I think, the 3-inch mirror at the end. And he realised, of course, that if you're trying to look in the mirror, and it's only 3 inches across, and you look in front of it, you can't see what it's looking at because your head's in the way. So he came up with the idea of having a little diagonal mirror so the light comes in and gets thrown out the side, and that's where you look. Quite a novel idea. You'd tend to think it'd block the light too much, but it doesn't really. You still get a lot of light coming around it, and depends on the size of that diagonal mirror as to how much gets blocked, but it really doesn't affect the image all that much. So here's the schematic of a Newtonian, Newton's telescope. So you've got in his case was a spherical but a parabolic mirror, which the light comes in, hits that, bounces back to the diagonal and out through an eyepiece, or out to an eyepiece. So you're getting all the light coming in there with a bit of a hole in the middle where the diagonal sits. The smaller you can make that diagonal, then the more light gets around it, and theoretically the better the image. But you don't really notice until that diagonal gets more than about 30% of the mirror itself, so which is quite incredible when you think about it. So you've got your parabolic mirror for some of them, you've got your flat secondary, and your eyepiece goes off the side there. This is a basic Orion scope. It's probably a 6-inch, I think, that one. And that's why they've got the eyepiece up that end. Some people that have never used telescopes say, what on earth is the eyepiece the wrong end for? What's going on? Because they're not used to the idea of it's a reflector, not a refractor. Then we've got, I'll call them hybrid telescopes. They're a combination of reflection and refraction, or some of them are anyway. This is what they call a Cassegrain. Basically, you've got two mirrors. Whoops, sorry, wrong button. Two mirrors. You've got a parabolic, what they call a primary, the main mirror, and there's a convex mirror up the other end. So the light comes in, hits the parabolic mirror, comes back, hits that, and that then throws it out through the end where you have your eyepiece up there. The 20-inch up at Stockport is a well, it's even more complicated than that, but it's basically a Cassegrain reflector. And you can actually put, instead of that there, you can put a diagonal mirror there as well and throw it out the side, so you can look at the end of it, or you can go up the side and look at it, depending which secondary mirror you've plugged in. Then you've got one that most people have seen around the place, the Schmidt Cassegrain. These have got a fairly complex corrector plate, which sort of does all the things to bring the light to the right spot. They go through, the light goes through that, hits your parabolic mirror, hits another secondary mirror which is convex as opposed to concave there, and then that throws it out the back to your eyepiece. So these are the ones that a lot of people have got nowadays. Basically what you're doing is you've got an F10 telescope. F10 means that the light coming through comes to a focus 10 times the distance of the diameter of it. And I'll explain that one in a minute. So you might have if you've got an 8-inch telescope or a 200mm telescope, F10 means that the focal length of it is 100 inches or 1.6 metres or whatever it is, depending which one you've got, 2 metres. And imagine trying to carry a 2-metre telescope around all the time. It's not much fun. I've got a little one at home which is a F18 4-inch, and it's over 6 feet long. So you can't sort of chuck that in your backpack. So effectively this folds the optics up and means that the telescope itself, instead of being 2 metres long, is only about that long, which is very convenient. Then you've got a different type of one, similar sort of thing. This is the Maksutov Cassegrain. the difference here is that it runs its mirrors. Whoops, I'll have to get used to this thing. The mirrors are both spherical. They're not put out to a parabola, and they've got a spot in the centre of the front one, which is, or not a mirror, that's the corrector plate. There's a little spot there which is aluminised. So the light comes in, hits your spherical primary, comes back, hits the spherical corrector plate and the little dot in the front, and then goes out the back. The classic of these ones is the Questar. There's a couple of them floating around the society. They're very expensive. They have been up into space and all sorts of things. They're built, they're sort of the Rolls-Royce. I had the Volkswagen version, which was the Meade version of it, but the Rolls-Royce, they're a lovely little telescope. I think there's one going up to Alpena next camp, so if you haven't seen one and you're up in Alpena, have to have a look. So again, we've got the focal length of it is between 12 and 15 times the width of the mirror. So again, it would be an enormously long telescope, but you've folded it down to make it a lot more convenient. And the Questar's got fancy base and all the rest of it, which we won't go into now. And then you've got the people that are into photography love this one, the Ritchie Creation. It's got hyperbolic primary and secondary, so it's a different shape again, slightly different, and it pretty well gets rid of what they call coma, which is distortion at the edge of the field, and other errors. So when you use it for your photography, you don't have to worry too much about trying to correct all this weird stuff that's happening on the edge of your field. So they're not cheap though. That one there, I'd hate to think how much that is. It's on a mount which itself is about 100 grand or something ridiculous. Okay, a little bit of background. Focal ratio. If you're into photography, you'll know what a focal ratio is. Basically, it's the focal length, which is the distance that the light has to go to be focused, divided by the aperture, the width of the telescope. So something that's got a focal ratio of f4, for instance, if it was a 200 mm aperture, the light, it comes to a focal point 4 times 200, 800 mm away. And that's what they call a fast telescope or a fast camera. And they go all the way down to f15, which is, you've got your 200 mm again, but it's 15 times that where it comes to the focus. And that's a slow one. The reason is that when you've got any given eyepiece, the lower the magnification, or if you like, the lower the focal ratio, the small focal ratio, you get a wider field and the image is brighter with any given eyepiece. If you put another eyepiece in which causes that high magnification, you're actually taking less of that image, and it's the equivalent of making the telescope longer but not as wide at the front. F4, F5, a lot of people have got F5 reflectors, like the, say, a 12-inch F5 is fairly common, and it's a fairly big telescope, but you need some correction with your eyepieces, otherwise the edge of the field, when you look at it, is a bit distorted. And there's different distortions that come about, but if you get a newer eyepiece which corrects for that, then you get a lovely wide field which is nice and sharp. But of course these corrected eyepieces cost more, and I'll explain them in a moment. Now we've got the slower ones, F11 to F15, like that Questar one I showed you before. They're good for high power stuff. Not so good for photography because you've got to wait longer for the image to develop or to get all the light that you want on your image. And the mid-range ones work pretty well either way. Mid-range, your Cassegrains, like the standard ones that people have around the place, they're the sort of the mid-range thing. Okay, very quickly, finders. If you've got a telescope that looks at a very small patch of sky, you don't necessarily know exactly how to point it there, so you use a little finder scope, which is a much wider field of view, and then you look at that and you can see, oh yeah, that's where I want to look. And if you make sure the finder is pointed the same direction as the telescope, you look through the finder first, think, yep, that's what I want to look at, and then you look through the telescope and that's where it is. There's different sorts. This is a little right angle finder, probably about a 60mm at the front, and you look in there and it's looking out. You use that. This is before you use computers and stuff, all that weird modern stuff we have. And then you have zero magnification finders, which are little red dot ones, or the fancier ones like the Telrad, which has a reticle which is projected up here, and you can see, if you look through there, you see that this reticle there, and you can look straight through. Two eyes, one looks there, one looks at the star field, and you can point to where you want it to look. Sometimes people use laser pointers and things like that, but if anybody's doing photography around you, they don't like that. They don't like green lines through their photographic field for some strange reason. And then we have eyepieces. Comment there, telescope's only as good as its eyepiece. It's the weakest, whatever's the weakest link, that's what you need to work on. And you can spend anything from $10 to $1,500 or more for an eyepiece. So depending how crazy you want to go. The magnification of the telescope, as I mentioned, is your focal length over the focal length of the eyepiece. So low power you use for looking, you've got a wider field of view, you're looking at star fields, you're looking at nebulae, various types, maybe globular clusters or open clusters, that sort of stuff, and you can see them a lot better wide field, so you use a low power eyepiece. Medium power, you look at zooming in a bit more on certain things, and then for high power, moon, planet, stuff like that. Generally speaking, on a good night, you don't want to go more than about magnification of about 2 times the aperture of the telescope. If you've got a 100mm aperture, you don't want to go more than 200 power on a good night. Generally, you'd go a lot lower than that. So this one is an 8-inch or 200mm telescope. Your maximum possible would be around about 400 power. If you've got, you see there, that's in inches, that's in millimetres, about 400. I wouldn't go 400 very much, ever. But the only time we've ever done that was up at Arkaroola, and absolutely brilliant night. And he's not here, but one of our members was yelling with delight because he was looking at Saturn at about 500 plus magnifications, and it was absolutely sharp. Okay, eyepieces, there's all sorts. If you buy a cheap telescope, you'll often find little eyepieces that come with it. They've got an H on them or a K on them. H is a 16th, 17th century Huygenian eyepiece, 2-element one. Works reasonably well for a long focal length telescope. Absolutely hopeless for a modern telescope, which is a shorter focal length. And then after some development, in the 19th century they came up with K, the Kellner, which is a 3-element, the orthoscopic and the Plossl. So these are the early traditional eyepieces. Nowadays we've got all sorts of fancy ones. In the 20s they came up with an Erfel. We've got one up at Stockport, it's often referred to as the awful Erfel. It works quite well, it gives you a nice wide field, not as sharp on the edges as you might like, but the newer ones, things like the Nagler, which came out in the 70s, early 70s, the Ethos, which came out about 20 years back, they give you this ridiculously wide field. So much so that with an Ethos, if you're looking through the eyepiece, you can actually look like that, and you can see the edges of the field of view, which I don't really enjoy doing that, but you can actually, it's almost like it disappears, and you can see this incredibly wide field, but you pay for it. I think the ethos, you can be up to $1,500 nowadays, depending which one you want. Okay, mounts is a problem. You need a good mount, and they're essential so that you don't bounce around, especially if you're looking at high power. And the different types are what we call the out-azimuth, which you often see with this one here. That's a little Meade Cassegrain or Schmidt Cassegrain. Small refractors, and they're often go-to nowadays. You get your dobsonian mount, which is basically the same thing. Basically, it goes up and down and sideways. It's very intuitive, easy to build, easy to use, and really solid. And attributed to John Dobson, who was an ex-monk, lived in California. He actually visited us about, 30 years ago, 25 years ago? A real character. But he made these things, and that really revolutionised amateur telescopes, because you could go really big and sit it on one of those mounts, and it didn't cost you a fortune, and you could lug it around a lot easier. And then, of course, you've got your equatorial mount, which is the telescope, or the mount, one axis of it points to the equator, try that again, it points to the pole, and the other one is at right angles to it, so it's like the equator. So effectively what it does is mimic the Earth, where you've got to imagine a line from the North Pole through the South Pole, and you've got the equator. These things do the same thing, but reverse it, so that as the Earth turns around, they turn the other way, and help you to be able to keep that star in the field of view. They can be a little bit more complicated than these ones, but some of them are fairly cheap. One of the problems for amateurs over the years is the cheaper ones, like the one they call the EQ1, is really a bit wobbly, and if you've never used one before, it's not intuitive. Whereas the up, down, sideways, out-as is intuitive, you know what you're doing. These ones aren't quite so easy unless they're motorised nowadays. Okay, just very quickly, binoculars. Two main types of binoculars. The more popular ones nowadays are what we call roof prism ones, and the older versions are the poro prism binoculars. It's a weird name, but the poros they're simpler, easier to make, and therefore cheaper for the same optics. Nowadays, you don't see too many of these above about the $200 mark, maybe $250 or so. And when you get into the more expensive ones, most of them are the roof prism types. The roof prism, you've got prisms that basically the light that comes through does a real little weird dance around and then shoots out the back. And it looks like there's nothing there, so you're looking through it and you don't notice there are any prisms in there. Whereas the poros are very basic with the prisms, and you can actually see the edge of them where the prisms have to fit in, so they're wider and funny looking. So basically with your binoculars, we've got two eyes. Looking through just one eye into a telescope is not natural. If you've got two eyes, you get better contrast, and you're more able to discern what's going on there. So binoculars are suited much more for the fact that we've got two eyes in our head. They give a nice wide field of view, especially if you're just using a handheld one. And yeah, generally, as I said, these ones are cheaper. These are some pictures of some basic ones. Little roof prism one there, your poro prism, which most of you have seen these around. And then you've got your binocular telescope, which is a whole different world, but I'll just put it there just so that we know they're available. One of the things with the roof prisms, because the light comes up and down and round and does a little dance and then shoots out, they find that the phase of the light coming through, because light sort of comes at a wave, like a wave front, the wave fronts get mucked up a little bit in all that reflection, and so the more expensive ones have what they call phase correction on them, which makes sure the wave front's coming through the same. Otherwise you tend to get not quite as sharp as they should be. So the cheaper ones don't have that, the more expensive ones do, and they're much sharper as a result and more expensive. Okay, You'll see on a pair of binoculars, they have something like 10 by 50, 8 by 42, 8 by 30, whatever. What that means is the magnification is the first figure, and the second figure is the width of the eyepiece, of the objective lens up the other end. So a 10 by 50 means you get 10 magnifications, and the actual end, the objective lens, is 50 mil across. So that's the first thing you need to know. When you buy a binocular, that's what that means. You get 10 power and it's 50 mil at the front. The exit pupil. Now this is where it gets a bit odd. When you look through a binocular, you hold it up, you'll notice there's a little round light almost in it that seems to be sitting on the actual eyepiece itself. That's what they call the exit pupil. That's where all the light has been concentrated, and that's what goes into your eye. Now, if you're looking through a binocular in the daytime, the pupil of your eye is probably only about 2 millimetres across. And when you look through a 10 by 50, you're getting a lot more light coming than your pupil will actually take, but it means it's a lot easier to put your head there and see through it. When we get a little bit older, they tell me that our exit pupils, which go out during the night time, don't go out as much. So when you were 20 or when you were 10, the pupil of your eye would open up to about 7 mil, or if you're Fraser Farrell, 25 mil. You would be able to see in the dark better. As you get older, the muscles change, things happen, and it doesn't always go out to the 7 mil anymore. If you're an old bugger like me, it might only be 5 mil. So the idea is you want the maximum amount of light that you can get into your eyes, and so if your pupil opens up to 5 mil at night time, you want 5 millimetre light coming in, which would make this one perfect. And it is quite nice, by the way. I throw this one in because sometimes Sky and Telescope and others have talked about a visibility factor when they're talking about binoculars to use at night time. And one of their writers about 30 years back came up with this idea: if you multiply the magnification by the aperture, you get a visibility factor. And the higher the better, was his idea. It works reasonably well. So if you've got binoculars that are 8 by 30, they're not going to give you as bright a view and probably as nice a view as maybe a 10 by 50. 8 by 30, it's only 240, 10 by 50, 500. It's not a linear relationship, but it does indicate the bigger the aperture, then the more light you're going to get in for the same magnification and better visibility of the thing. And finally, traps for young players. People don't often know how to use binoculars, how to properly use them. I've got a pair here. These are my little Poro prism binoculars. When you're looking through them, your eyes are a certain distance apart, and everybody varies in that. So for children, it might be, you might have to pull them really close together so that both eyes go through it. For adults, it's a lot wider. This one will go out to about 75 mil between your eyes. Most of us are around the 60 mil mark. So the first thing you need to do when you hold up binoculars is to make sure that the light is coming from that side into that eye, that side into that eye. And if you're looking in the distance, the images will merge and you'll see a circle. It's not like in the movies where you see a funny little figure 8 or something weird like that. If you see a figure 8 when you're looking at a distant object, then you need to adjust the what they call the interocular distance, the distance between the two pieces, so that it's coming properly into your eyes. When you're getting up close, it changes. You will find that figure 8 will come out as you get closer because there's too much of an angle between the two of them. But generally speaking, you get a pair of binoculars, you look through them, you wind them back or forth until you've got a nice circular image. That's the first thing. You want your eye separation, well, that's the second one there, sorry about that. Then when you focus it, most binoculars, one of the eyepieces twists a little bit and the other one doesn't. The twist in one of them is what they call for the diopter adjustment. Our eyes we're all different. We all focus slightly differently, and the opticians talk about diopters as an amount that you have to move things to focus your eyes. If your right eye is slightly different to your left eye, then you'll find that when it's in focus for one, it's not in focus for the other, and you have to adjust the diopter. So what you do is you focus with this, in this case, you focus the left eye, perhaps you could block the other one, make sure it's in focus, and then you look through the other eye and you twist it until that's in focus as well, without touching the main focus. So both sides are then focused properly, and then you leave it alone. Then when you use the main focus, they'll stay in focus for your eyes, because your eyes are slightly different. Most of us, they're fairly close. Some people I've heard of about 6 diopters difference between one eye and another, and sometimes if you had surgery or something like that, you really need to be able to do that quite heavily so that both eyes are focusing at the same spot. So when you give a pair of binoculars to somebody and they've never looked through them, first thing they need to be able to make sure both eyes are looking through. Secondly, that it's focused for both eyes, and you've got those 2 adjustments as a result. Okay. I find with children it's really hard to get them to look through binoculars, particularly if they're under about 6. If you go to a school and you've got binoculars, forget it for little ones. And they'll do things like they'll shut the wrong eye and look through a telescope, so there's the eyepiece. I can't see anything. But that's not just children. I've had 50-year-olds do that too. Okay. What can you expect to see? I've got a couple of photos up the top which are not what you really see in a telescope. That's the Orion Nebula, Jupiter of course, and that's the Andromeda Galaxy. You won't see it with the colours and everything else like that in a telescope. Sometimes people get disappointed because they see all these things on the internet and they think that they can see all the colours in there, they think they can see all the colours here, but it's nowhere near as cut and dried as that, and the colours are often distorted. When NASA puts out pretty pictures of Jupiter, for instance, they distort the colours. So what you see is not what you see in a telescope. In a telescope, when you're looking at Jupiter, you're more likely to see something a bit like that. Now that seems a little bit out of focus, but that's often what you can see. You can see the great red spot, you can see some detail in it, and as you look at it, it'll come in and out slightly, and you'll be able to find out all sorts of detail, but you don't see those sorts of colours like that. The Orion Nebula, yeah, you can sometimes see a little bit of a sort of a greeny tinge or a reddish tinge if it's a really dark night and you've got a big telescope, but generally you're looking black and white for these things. But I can't show it there, but you'll see the trapezium, which is the 4 stars in the middle in a telescope, and you rarely see that in photographs. You can actually see sharper detail with that sort of thing with a telescope. And Andromeda is nowhere near as colourful as that as a centre. It's much more like that when you look at it. And you can just make out dark lanes and so on if it's a really dark night and you've got a good telescope. The planets, similar sort of thing. Mercury, you'll see the phases of Mercury as it goes around the Sun. Venus, likewise, it goes from about that size up to about that size, depending where it is as it goes around the Sun. It can be quite sharp, but you won't see any detail, or very rarely see much detail, either on the surface or on the clouds. Mars goes from sort of there up to where you can start to see stuff, depending how far away it is, but it can be a real disappointment for Joe Public because they've never seen it. They look at it and you can't see much at all because it's not very big. And just another shot of some of the planets. So there's what Jupiter looks more like in a telescope. In a binocular, you'll see a bright circle with the moons, and that's what Galileo saw. So he was able to see that they moved all the time. And you look at it within a couple of hours, and those dots will have moved. So with binoculars, you can see the movement of the moons, but you can't see any detail. Saturn, in a telescope, you can see the rings. At the moment, they're almost side on, so you wouldn't see it like that. But you can see things like the Cassini division in the rings, And on a really good night, you can see a little thing there called the Encke division, which is only about 15 kilometres wide, something like that. I have seen that in a telescope, which is, when you think about it, something so far away is pretty amazing. But so you can see that. Good old Uranus and Neptune just look like little bluey green stars because they're so far away and so small. Okay, I think that's enough waffle from me, and I think timing's about right. So any questions, thoughts, corrections? How much? How long's a piece of string? Yeah, Peter's saying, how much are binoculars to buy? Your basic Poro prism binoculars, these are little ones, these are 8x30s. The reason ones start about the $100 mark. A lot of people would recommend, for instance, if you want a reasonable binocular to look at the stars, you look at something like a Nikon, around about the 200 mark, that sort of thing. So it varies a lot. Your basic Poros are you get what you pay for. So if you buy a really cheap one, you'll be able to see stuff and it'll be okay during the day, but you're not going to be able to see a great field of view at night. Your centre will be sharp, but you'll often find the edges are quite fuzzy and you get colour in them as well. But so the, which one is it called? There's the Nikon Aculon, and then there's their EX, is it? EX, I think. They're sort of around the 200, 250 mark, and they're actually quite nice for general use. If you want one of these, the price has just gone up. These are 1,500 at the moment, which is crazy. That's a Swarovski Hubitch. I brought these two along just for interest. I was lucky enough to pick up these ones on Ice in Space a while back. There's a guy who's over in Western Australia who is a FIFO, and he's got lots of money, and he buys all these fancy stuff, keeps them for a little while, and then flogs them off on Ice in Space. So I got these ones. This is a Zeiss SFL, which is their latest moderate to high range binocular, and this is a Swarovski. This is the little Hubitch 8x30W. 70 plus years between the two of them in terms of their design. Both of them give amazing views. There's all sorts of different reasons for that, which I won't go into now. But this one was originally developed in about, I think, 1948, thereabouts. It first came out. It still looks the same as that 1948 version. But it's got much better coatings nowadays, and they've sort of tweaked things. It's about as good as you can get from a Poro prism. And this one, it's actually Zeiss make them all over the place now. This is actually made in Japan, and they both give about the same field of view. This one's just a tad sharper on the edges. This one has about a 96% light throughput. So basically, in the old days, when light hits a lens or hits a bit of glass, a certain amount gets reflected, a certain amount gets sucked up by the glass, and then the rest of it comes through. So if you don't put coatings on the glass, you might get 70-ish% through a single lens because of all that stuff. And when you get multiple lenses, each of them is only getting 70% transmission of light, that adds up real quick. So if you've got half a dozen lenses, each of them only transmitting 70%, you might only get 30 or 40% of the light getting through from early binoculars. This one's got multiple lenses, but you get 96% going through because of the new coatings they put on them. This one's pretty similar, up over the 90 mark. So they're super bright for the aperture compared to the old days, but in terms of the actual design of them, there's over 70 years between them, which is kind of crazy. I always think it's great to have at least one pair of binoculars if you've got a telescope. And often people say maybe a 10x50, thereabouts, just so that you can have a general look around, particularly if you're doing photography, so you can muck around and look at things. But also you get a different sense of what's out there when you're looking through binoculars. You get both eyes are coming into play. you go up to places like the Flinders Ranges and it can be mind-blowing. Those little habitch ones, when I took them up there first, I could see, looking at Orion, and there's a huge nebula that goes around Orion called Barnard's Loop. And I guess you saw that in the 8x30 binoculars and could follow the whole thing around. There's no way you'd see that in a telescope. You might if you do a long photo, a wide-angle photo of it, you'd see it then, but you wouldn't see it in a telescope. But with the binoculars, you can pick up things like that. When I looked at the large and small Magellanic Clouds with those little binoculars, I could see them much bigger and stuff going out right to the edge of the field, which is an 8-degree, 9-degree field, just with those. And there's no way you'd see that in a telescope because you're looking a lot smaller. So yeah, it's always a good idea to have one on board. And if you can afford a couple of $100 to make sure you get a reasonable one, yeah, they're great. Yep. Yep. Yeah, well, I mean, that's